Hi everyone, we are Group 14. Our final project aims to utilize deep learning methods for 3D reconstruction. Let's begin our final presentation. The approach we use is based on the methods described in this paper, splatter image. In the following presentation, we will introduce the concepts, framework, and results. Here is the outline of our presentation. First, we will introduce what splatter image is. Then, we will briefly explain some recent approaches to 3D reconstructions and related work. Next, we will describe the methods we used, including the principles and framework, followed by the results and discussion. Lastly, we will showcase the results of our own demo. So, splatter image is a method designed for ultra-fast single-view 3D reconstruction of the shape and appearance of objects. This approach is based on 3D Gaussians and leverage the rendering quality and speed of Gaussian splatting. Splatter image introduced a novel design to achieve efficient 3D reconstructions. The main ideas are as follows. First, it maps 3D Gaussian parameters such as opacity, position, shape, and color to each pixel of the input image using an image-to-image neural network. Second, Gaussian data is stored in a 2D structures, avoiding the computational cost of directly 3D convolution. Third, a UNet model is used to capture fine details, improving reconstruction quality. And this figure is describe the outline of the model. Based on the above model design, splatter image exhibits several notable characteristics. First of all, splatter image demonstrate high efficiency. It can process standard 3D datasets using only one single GPU and optimizing for perceptual metrics like LPIPS to ensure high-quality reconstructions. Second, it offers excellent scalability. The method supports multi-view reconstructions by combining Gaussian mixtures from multiple views into a common coordinate frame. Additionally, lightweight cross-view attention layers enable effectively communication between different views, further enhance performance. To summarize, the contributes of this work are as follows. One, it supports Gaussian splatting to a learning-based approach for monocular 3D reconstructions. And second, introducing a simple, efficient, and high-performance 3D reconstruction methods that operates at 38 FPS on the standard GPU. Last one is extending the methods to support multi-view reconstructions, achieving state-of-the-art performance across benchmarks, including real and multi-category and large-scale datasets. In recent years, there have been several methods for single-view 3D reconstructions, each with its strengths and weaknesses. Let's take a look at these approaches. First, we have implicit representations. While they are popular, they tend to be so slow to render. It can take up to 2 seconds just to process a single 128 by 128 image. To improve on this, follow-up works has used explicit Mosul grid representations. This directly encode opacity and colors, which makes rendering faster, but they have their own issue too. Scaling with resolution becomes a problem, and they require knowledge of exactly viewpoint of each object, which limits flexibility. Next, we have triplane representations, which strikes a balance between rendering speed and memory usage. It's fast enough for single-view reconstructions and works well with a large dataset, but it comes at a cost. It needs hundreds of GPUs and multiple days of training, which is quite computationally expensive. Finally, let's talk about 3D Gaussians. This is where splatter image shines. It has several advantages over the previous methods. First is its real-time rendering. Splatter image predict a mixture of 3D Gaussians in the feed-forward manners, which means it can render in real time. And second is its cost-efficient training. It's also much cheaper to train. It only needs 1 to 2 GPUs, and which is a huge improvement over other methods. Third is its high-quality result. Despite being computationally light, splatter image still delivers high-quality reconstructions. And the final one is multi-view fusions. Splatter image can fuse multiple views to enhance reconstruction quality, making it adaptable for different scenarios. And also, one of the standout feature is that splatter image can generate 360-degree reconstructions directly from just one image without needing additional 2D or 3D impeding network. Another approach used in the field of 3D reconstructions involves point clouds and probabilistic methods. For 3D reconstruction with point clouds, this approach is commonly used for high-quality multi-view reconstructions, where techniques like 2D impeding networks are employed for hole filling or isotropic Gaussians are used for better representation. However, a key limitation of these methods is that they require ground truth 3D Gaussian point clouds, which can make them less flexible and not always applicable in real-world scenarios. In contrast, our approach utilizing 3D Gaussians can model all parts of the object, not just the visible one. This enables us to achieve 360-degree reconstructions, providing a more complete and flexible solution. Moving on the probabilistic 3D reconstructions, many recent methods treat single-view reconstruction as a conditional generation task, using techniques like differential models for novel view synthesis. While these methods can produce impressive results, they often suffer from the major issues. Generating image without underlying geometries can lead to an image flicker, which negatively impact the quality of the output. Our method, on the other hand, focuses on the deterministic reconstructions, ensuring more stable and reliable results. And this makes our approach complementary to generative methods, as it has the potential to improve both speed and quality when combined with other techniques.
Hello everyone, my name is Yuan Wang. Here I will introduce the method in the paper. 3D Gaussian spreading begins with a structure from motion process, where corresponding feature points are extracted from multiple 2D photos to estimate an initial 3D point cloud and the position of the cameras. Based on this point cloud, the initialization state calculates the parameter of 3D Gaussian distribution, including position, shape, color, and transparency. This state smooths and connects the object shape, ensuring it is continuous and well prepared for subsequent options. Next, the 3D Gaussian distribution are projected onto a 2D image plane by ordering them according to depth and align them with the camera's viewpoint, simulating how a physical camera will capture the object from a specific angle. In the rasterization rendering step, each 3D Gaussian distribution is transferred into a renderable pixel, generating a 2D image that visually represents the 3D Gaussian model from a given perspective. To refine the result, Adaptive density control adjusts the size and density of the Gaussian distribution based on discrepancy between the rendered image and the original photos. This ensures that blurry regions are enhanced, sharpening edge and details to better align with the original input image. Finally, the rendered 2D image retains the complete 3D Gaussian parameters for each pixel, allowing this parameter to be back-projected into 3D space, thus enabling the reconstruction of the entire 3D model of the object. Each pixel in the splatter image encodes the parameter of the corresponding Gaussian point, including depth d, 3D offset delta, color C, C, and transparency sigma. From these pixel parameters, the corresponding 3D Gaussian distribution can be reconstructed. The image plane coordinate of each pixel, u and v, combined with its dips, representing the pixel position along the camera ray, enable the computation of its initial position x, y, z in 3D space. The inclusion of the 3D offset delta offers enhanced flexibility for handling occluded region, ensuring better reconstruction of the hidden detail. Once all Gaussian points are determined, the total spatial distribution is computed. During rendering, the accumulated color values are obtained by integrating the color along the ray as they traverse the 3D scenes. This process results in a flexible 3D model that can be rendered from any desired viewpoint, allowing 3D Gaussian distribution to produce synthetic 2D images that match different perspectives.
Hello everyone. Next, I will presentation experiment session. First, I will introduce the dataset. The dataset is mainly divided into two parts, single class and multi-category. ShapeNet SRN serves as a standard benchmark for evaluating single-view 3D reconstruction. In this paper, the author used two categories, cars and chairs, to report the result. Additionally, Core3D involved two types of real-world objects, fire hydrant and teddy bears. The following datasets are used as a benchmark for multi-category evaluations. The evaluation of the results will follow the same criteria as the related work. We will assess the quality of the reconstruct image based on the following metrics. Next, we evaluation the method using the ShapeNet dataset for single-view 3D reconstruction. This method outperforms all reconstructors in terms of SSIM and LPIPS, producing sharper and higher quality new views. Unlike other methods, we require only relative camera poses, instead of absolute or canonical poses, making our approach more flexible. In the table, we follow the multi-category ShapeNet protocol to compare the performance. The results show that our method consistently outperforms baseline method across all metrics in a ShapeNet setting. For example, in categories such as cars and chairs, our approach achieves the best TSRN, SSIM, and LPISP sources. In this part, we evaluate our method on two datasets, Core3D and Observer's LVRS with Google scanned objects. Starting with Core3D, our method outperforms PixelNerve across all metrics, including PSNR, SSIM, and LPIPS. It's not only generates sharper and more detailed image, but is also 100 times faster, demonstrating significant improvement in both quality and speed. Next, our observers LVIS and Google Scan objects. As shown in the table, our method called splatter image achieved better PSNR, SSIM, LPIPS source compared to OpenLRM, even when using internet collecting image with background removed and resized. Our approach remained highly effective, showcasing its adaptability and robustness. Remarkably, our method trained for 7 GPU days, enabled to compare with OpenLRM, which used hundreds of GPUs for several days. Next, we evaluate our model for 2-view 3D reconstruction using the ShapeNet SRN hard dataset. Our model was specifically trained for multi-view reconstruction, focusing on 2-view predictions. Unlike previous methods that often rely on absolute camera poses for reconstruction, our approach addresses a key limitation in real-world scenarios. Absolute camera poses are typically unknown, which restricts the practicality of such models. In construct, both our model and pixel nerve are capable of handling relative camera poses, making them more practical and adaptable for real-world applications. As shown in the table, our method achieved the highest score in both PSNR and SSIM, demonstrating superior performance in this two-view setting. Next, we will discuss the ablation study. This study involves systematically removing certain components of the model to evaluate the contribution each part makes to the overall performance. As shown, removing any components result in a certain degree of homogeneous degradation. This indicates that every part of the model plays a significant and indispensable role in the effectiveness. Finally, let's highlight the key advantage of the splatter image method. Its remarkable efficiency during both training and testing. As shown in the forward path, this method achieves the fastest performance across all compressions, demonstrating its exceptional speed and effectiveness. Finally, we use our own photos and generate a 3D image using splatter image. The result of our demo is shown. The left image is the original photo, and the background is already removed, while the right image shows that animation created from the Generate 3D PLY file. The image size we used was 564 times 2360. Since the image was quite large, it took about 2 minutes to generate, but with just one image, we were able to get a really good 3D reconstruction. This shows that the model and method in this work are feasible. This concludes our presentation. Thank you all for your attention.